Hello, this is Jack Jackson. In this video, we're going to talk about kites in non-Euclidean geometry. So here you can see my geometry collected resources in GeoGebra. And if we go to quadrilaterals, this classification of quadrilaterals investigates lots of different things, including kites in, um, in Euclidean geometry. Here we see some other things here for some other investigations of kites in Euclidean geometry. Let's just start with that actually. So if you can see, this one kind of shows some properties there of kites. You can kind of see this sort of animated. And so notice they had a bunch of interesting things. They're defined by two pair of congruent sides. They're adjacent, congruent. Um, and notice, but we have some congruent angles there, opposite angles. We have congruent angles with a diagonal. We have a perpendicular bisector in the middle. So we got several different interesting things there. You can kind of see that dynamically. Okay, we investigated this in some detail in our last thing, our last few videos. And this one is a similar kind of thing, which looks at kites in Euclidean geometry. But what about kites in other geometries? So let's look at my thing here for kites in hyperbolic geometry. Now, if you're following along my videos, in the last video, we actually proved properties of kites for Euclidean geometry, and the proof was exactly the same for hyperbolic geometry. We used the same steps. So if you notice, this is the same basic setup, and it's constructed the same way that we did a kite in Euclidean geometry. We start with points A, B, and C, which can be any free points, can be placed anywhere. Looks like this is breaking in some places here, but we have this. They can be basically anywhere. And to get D, we found it by getting two circles, one circle centered at B of radius centered at A of radius AB, and one circle centered at C of radius BC, and they intersect, of course, back at A and only at D. Let's actually just draw those circles in, and just so you can see what we're doing. We want to center it at A and go through B. We want to center it at C and go through B. Okay, and of course they intersect at B, but they also intersect at D as well. And there's our point. That's how we basically find this. And so remember, these are hyperbolic circles. So things look a little differently than they do in Euclidean geometry, but the basic setup of how it's constructed is the same. Notice you get basically the same things here. Notice I've measured the sides here. These blue sides are congruent. The two red sides are congruent. You can see from their hyperbolic distance measurements up here. If I move this around here or here, these numbers change, but they stay the same as each other. If we look at the major diagonal, there it is, along with its length. There's the minor one there. Notice that we have a pair of congruent interior angles here because we have these two triangles are congruent by side, side, side. So they got a better pair of congruent interior angles. We have angle bisectors on both ends here. Something we had here. These two are the same. These are the same. We have the line containing the major diagonal. When you put it with the minor diagonal, we see it's a perpendicular bisector there. That's a right angle, and BX and DX are the same length. Here are the measurements right there. Notice that they're the same measurement. They may not look the same because of the way measurements are done in hyperbolic geometry, but they actually are when you look at them in this thing. So we get exactly all the same results there for hyperbolic kites as we do for kites in Euclidean geometry. How about spherical geometry? Well, I've got an investigation for that one too. Okay, So again, how do we construct D? We take A, B, and C to be any free points we want. And to get D, we take a circle centered at C of radius BC. That's this one. And then we take a circle centered at, no, that's the one centered at A. So one is centered at A of radius AB is this one. And then the one centered at BC of radius, centered at B, centered at C of radius CB, that's this one, okay? Let's do a couple things. Let's go ahead and just make this one, just to make this a little bit more clear which one's centered where. See if I can select it. Let's go ahead and make that one blue and make the other one red just to match with the radial segments that we have there. Okay, so that's the way of constructing it. It's constructed the same way that we do it in Euclidean geometry with the definition. Now we also have a line containing the major diagonal. There it is. And it turns out that this has a reflective symmetry over that line. And it turns out that these two triangles are congruent, again, by side, angle, side. And so if we look at the major diagonal with it, those two triangles are congruent with a reflection about this line here. Okay, so among other things, that means you have a pair of congruent interior angles right here. And we also said that we have bisecting angles here. So the major diagonal bisects the angles on both ends. And if we take the major diagonal and the minor diagonal, or if we take the line containing the major diagonal and minor diagonal, whether it's out here or out here, we see that it is actually a perpendicular bisector on both ends. And the same proofs work, same observations, same proofs work for spherical geometry that we saw for Euclidean geometry. So kites work basically exactly the same way in Euclidean, spherical, and hyperbolic geometries. How about taxicab geometry? What do you think? Well, by this point, you should already have a suspicion because we don't necessarily get the same congruence properties, right? Well, all of this was very much based on congruence properties of triangles that we get when we make the major diagonal on the sides. Well, we know that doesn't work in the side angle side postulate, the side congruence theorem, the angle side angle congruence theorem. We used all of those in the proofs of the kites property. None of those work in kites here. You can build it exactly the same way. I think I don't remember if I did this the same way or not, but you could build it basically the same way. But notice that if you measure things as taxicab distances, AD and AB are the same length, DC and BC are the same length, but you can see these triangles are not going to be congruent in general. If we were to measure, so we're just measuring the angles is enough to tell us like this angle here should be congruent to this one if they were congruent triangles, which they're not. And so you see these are not perpendicular for the nor are they bisectors for the diagonals. So that right there, just that one example is enough to show you that you're generally in taxicab, the kite theorem doesn't work. Now there is a subclass of kites where it does work, and these are kites that have symmetry, but you have to be a little careful about this. The angle that we have let's say the diagonal, major diagonal makes with the horizontal makes a difference, and there are only certain ones that work. So it turns out that if your axis is horizontal for your major axis, then in fact we do get all of our normal things about kites, that these are congruent as taxicab distances these links are the same, the two red links, and the two blue links are the same. And once again, we get a perpendicular bisector here. We get all of our normal properties of kites. But notice that the major axis needed to be horizontal for that to happen. If the major axis is vertical, that also works out to give us that same situation that we would have. And it's really because of these two particular examples, a reflection about a vertical or horizontal line, a Euclidean reflection about a vertical or horizontal line is a congruence mapping in Taxicab, whereas reflections about most lines, they're not a congruence relationship, congruence mapping. If the angles are at make a 45 degrees or pi over 4 angle with a horizontal, in other words, they have a slope of 1 or -1, then that also works as well. So once again, those reflections over those lines turn out to be map a triangle to a congruent triangle as well. So these work out. So these particular ones work out to have all the properties that a normal kite would have in Euclidean geometry. Okay, but kites in general do not have that property. So kites in general don't have the normal properties there. Okay. So once again, taxicab geometry operates very differently than the other two geometries.